So I'll get started pretty quickly here. So I'm going to, I've been sitting here for a couple of days looking at a lot of research papers, and I'm going to bring a bit of an operational perspective to some of this stuff. Talk about what it's like in the operational world in terms of moving this forward. A couple of things you should note, those of you from the US, sort of NOAA is the equivalent agent to the Meteorological Service in Canada, but in Canada we don't issue flood forecasts out of our national agency. They're done by the provinces. But we do our hydrometric monitoring just like the USGS does in the US. In Canada, we do our hydrometric monitoring as a national cost share program. So some similarities with the US, but some differences as well. So I'm going to talk a little bit about our hydrological services, where we're going in Canada, talk about the flood, the context of hydrometric monitoring, what happens after a flood when things get wiped out, talk a little bit about the hydrometeorological prediction that we did for the event, and some conclusions. So to put some context on this, this is the sort of flooding estimates from a bunch of sources that we've put together in Canada, mostly from our public safety agency. Just to point out that over the years there's been significant floods in Canada. This is decadal sort of averages here. Significant, the number of floods, the number of evacuees, the deaths, and the cost. And I put 2013, I only put the values associated with the Calgary flood based on the press. So you can see the Calgary flood far exceeds anything we've seen before, even on a decadal basis. So when we look at the floods for the current decade, and we start thinking about the ones on the Assiniboine, and we had a lot of flooding in Canada over the last few years, it'll be an unprecedented year in terms of flood damages in Canada. There's no doubt about that. This is the National Hydrometric Program, so we're a cost share program. We've got all the provincial flags up there too. Much like the USGS operates, we cost share, so essentially the Water Survey of Canada does the hydrometric monitoring on behalf of the provinces and territories. We charge them for the privilege, and so we have a cost share agreement to do that. So that makes it a bit of a challenge for us, because from a flood forecasting perspective, the provincial agencies do the forecasting, they rely on our data, and so there's a strong collaboration between the federal and provincial agencies when there's a flood, because obviously they need us to get out there and take the measurements. So the flood event, it was on June 20th, the City of Calgary declared a state of emergency. WSC stands for Water Survey of Canada, continued in full flood response. What that means is basically we've got to get out there, repair stations, put up temporary stations. You actually have to take the measurements once in a while, right? The rating curves go off the charts sometimes, so our folks go in there and actually take the velocity measurements if it's safe. If it's not safe, they can't go in the river. So there's a lot of challenges from a hydrometric perspective in taking this data. So, you know, those of you who do modeling, and I do a lot of it as well, you should always look at the data very carefully when you start doing the modeling, right? I've seen people try to pinpoint, you know, the flood peak. Sometimes it's a bit of an estimate and a guess, right? So be careful when you're doing your modeling. You may not have to worry so much about getting that peak exactly right. So this is just some examples of some pictures of we have a lot of infrastructure in the mountains, you know, in the west of Calgary there. So this is one of our stations that was completely wiped out by the flood. All that remains there was a stilling well, so that's gone. Here's a typical sort of cableway structure here. We have cableways to cross the river when there's high velocities. That cableway is no longer there, so that's a $80,000 investment that's gone downstream. Here's an example, and you can see kind of how our cableways actually are installed. They're fairly robust structures, right? That was a fairly new cableway with 3 wires and, you know, well placed on the ground. And after the flood, there's nothing left but a concrete block. And then, of course, the whole issue for us from a rating curve perspective is once the flood's gone through, the regime's changed, the hydraulics have changed, right? And so you got to reestablish rating curves and relook at how you're going to do things. And that's a bit tricky too. This is our system, and I know it's a convoluted diagram, but the purpose here is to show you that this is our production system. And so when you look at flow data, I've seen so many people tell me, oh, you know, you measure flow. Well, no, actually we don't measure flow. We measure water level. We estimate flow with the model, right? And so there's a lot of work that goes into estimating flows, right? And that's our system that sort of does that. And we're moving to a real-time system in Environment Canada, and I know the USGS is doing the same thing, and they have for many years. So you can imagine, with a rating curve, what happens is you go out in the field, you take a measurement, you realize something's changed, a beaver dam or whatever's come in to change the hydraulics of the river, right? Our technicians go, okay, well, our point doesn't plot on the rating curve anymore. We have to do a rating curve shift. We have to adjust something. We have to do a new fit on the rating curve. They usually do that after the fact, right? And so typically you publish data eight months after you've actually collected the data, 8 months to a year. And so when we're moving to a real-time system, we're trying to update the rating curves as soon as we can, right, to get the best possible estimate of flow on a real-time basis. And so that's a bit of a paradigm shift for an organization like ours, and we're working on trying to do that. So there's a couple of entry points here where we have to do things. So now we're looking at electronic field notes so that when the tech goes out and take a measurement, it gets entered in the system right away. It automatically gets updated, enters the computers. If there's a rating curve shift, it gets applied right away, and that becomes your real-time flow. So it's kind of a near real-time system. You can't do it at t=0, but you can certainly do it maybe a day later. And so that's kind of where we're going, and that should help with some of the flood forecasting issues that we see arising from the provinces. But it's not trivial, and so people should understand that. The other thing is when stations get wiped out, there's not much you can do because you have no data. And so we go and we survey high water marks. So there's, I think there was 15 stations that got completely wiped out during the flood. And so we go back in and we survey high water marks. We use the slope area method. It's a standard USGS and WMO. There's a couple ways to do it. And we also run HEC-RAS to estimate the peak flows. So we've done our preliminary calculations. So you remember this was 2013, so we're just finished our calculations now. We actually run them through a consultant, so we kind of double check our work. The estimates are in increments of 50 cubic meters per second, which is a lot of water, and that's the best we can do with that kind of a method. And we expect the final peak flow results should be available in spring 2015. So one of the things we looked at after this flood is, could we have provided lead time to the water survey people? If we would have known 5 days ahead that this was coming, right, could we have prepared better? Could we have moved things out of the way or whatever? And we really have no systematic system to do that. And we've been working in Canada for a long time on a water cycle prediction system. It's a fairly robust system. It's part of our operational numerical weather modeling system. GEM is our numerical weather model. We actually have a NEMO model. That's an ocean model that we run on the Great Lakes as an example. We have H2D2. It's a 2D hydrodynamic model that we've actually operationalized in our supercomputer as well. And we've got this system called MESH, which it's been around a long time. We've done a lot of development work on it. And that's the hydrological model that we've developed. And we've done some good studies with the U.S. on the Great Lakes as an example, looking at net basin supply for the Great Lakes. And we're able to replicate at least monthly flows into the lakes reasonably well in a hindcast mode. So that's the system we're looking at operationalizing for the water survey, so we can get actually 5 or 10 day ensemble forecasts for our techs to be able to go in and do some work. The other thing we do in Environment Canada is the precipitation analysis system. Some of you might be familiar with this. So we basically take the 6 to 12 hour forecast out of the numerical weather model and look at the gauge network as well and do basically an optimal interpolation. We started adding radar data to that, now ground-based radar data to that, and that's really our best data estimate of flow. You got to remember Canada's a big place. We don't have a good density of network of gauges, and so we need to do something. So we find that with the optimal interpolation, we get pretty good results. So this is some results from CaPA, the precipitation map, compared to sort of an interpolated map on the left-hand side here. So it's not perfect. I think we'd underestimated the total amount of rain accumulated over that period. But the maximum precip only came out at 221 millimeters as opposed to 300 millimeters, which was measured from a gauge. So there's some issues with it, but it was actually pretty good, and we actually used it to force our model. So we decided to not go with the observed values, but go with the CaPA to do the model testing. Just to give you a sense of the event, so this is the North American Ensemble Forecasting System. So this is looking at the forecast of just precip, and you can see around the Calgary time there, the 20th, 21st, when the big rainfall events happened. There was a pretty good lead time on some of this. We had some good idea that this was coming. There's a bunch of other evidence. I won't go into details here, but we had a pretty good sense of what was happening. So from an operational perspective, I started looking at it from a water survey perspective. It would have been nice to have 6 days to get ready for this event, right? And we should have. And we have all the modeling tools in place to do it. And so what we did after the event was actually look, and could we have actually done something with our technicians and with our models to make people a little bit more aware of what's going on. So this is the regional ensemble prediction system. The 3-day lead time, and it pretty much nailed the event to a large degree. So again, even 3 days for us would have been very useful. So I'll talk quickly about the modeling system. There's lots of posters around and on the system. This is the system we've developed in Canada over the last, I don't know, I'd say since 1996 we started working on this through GeoX. Essentially, it's a coupled land surface hydrology model. It works it takes the Canadian land surface scheme. It uses sort of the approach taken in a more engineering model that was developed at University of Waterloo, the Watt flood model. It has a routing component. It has it uses tiles for land surfaces. Lots of details I can go into, but I won't have time. But we think it's a very appropriate model for Canada. We actually think it works reasonably well. We've tested it at a bunch of basins, including the whole Great Lakes. We're now testing on the South Saskatchewan River Basin and the Mackenzie Basin as well. And we think it's a very good approach to dealing with the hydrology in Canada. The way it works, just to break down a little bit, is conceptually the way we designed it is we said each of the tiles in the model, if you look, it's a grid model, right? So each of the tiles, basically you run a land surface scheme. But it's a sloped land surface scheme. It's a little bit different, and so it accounts for interflow and drainage as well. And then you route between each of the grids using basically a kinematic wave model. It's just called Watt route. Derived from the Watt flood model. So it's a very basic structure, but it does have a lot of hydrology in it. And the way we designed it is to make sure we could allow for energy and water transfer between these tiles. So these tiles can be landscape types, they could be elevation bands, it can be whatever you want them to be, right? And so we wanted to build a lot of flexibility in the model, and we think that's the way to go. So basically the approach in the mesh modeling was we used an existing watershed mesh model from the South Saskatchewan. We converted CaPA precipitation into another format so we can read it, calibrated the model, and for basically a small period of time, and we tried to model so it was kind of an out-of-the-box approach to looking at the floods, and we were actually surprised with the results. So there's the calibration period there. We had a terrible Nash-Huck cliff, but when we validated the model, we got some pretty good results. So we used an engineering model, Watt flood, to try, we did a long calibration period. We thought we'd get pretty good results with that. Turned out we had to kind of recalibrate the model to get the peak flow right. So our peak flow with the Watt flood model was only at the 856 cubic meters per second, when the true peak flow was closer to around 1,200. So what we kind of learned from that is this model has a bit more physics. We think it actually needs a little less training, I guess. In terms of optimization. And so, it was a significant rain on snow event, and we could manage to simulate things reasonably well, kind of out of the box with just the minimal calibration. So we're pretty pleased about that. So we want to move towards a more operational system down the road here. So just a couple of conclusions, I guess. Many years of systematic model development with mesh since 1996. The model is very similar to something like WRF Hydro. Those of you in the US know that system. Essentially, the mesh modeling system appears to have reasonably simulated the 2013 event with minimal calibration. I think it's important to understand flow data collection during the event provided significant challenges for the hydrometric staff. So when we go back and start looking at this data, just keep the context in mind or any flood event actually, you should keep the context in mind. But we need to move to a real-time flow estimation system. So what we're really trying to do is marry the two models together. Both what we've done, with the real time from the water survey, and then the forecasting system together, and bring them both into one operational system. Many hydrological challenges, and I don't want to underestimate that. Just because you get a good model result, you shouldn't just walk away. And I think I'm going to refer you to, John gives a great talk on hydromythology. There's still a lot of hydromythology in our model. So don't take it as any kind of gospel truth. So I'd refer you to John Talk. And we have a lot of posters on mesh, so I'd encourage you to go look at some of the mesh posters around there and see what you think. So, and I'm just on time. I got 47 seconds. Thanks.